check, 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 check.
දැන් යන්න පුළුවන්නේ. වැඩි වගේනේ නැද්ද? Good morning, everyone. So a bit late, but Archimedes theorem. So the last topics, couple of topics of hydrostatics. So let's start this Archimedes theorem. You all know Archimedes. How do you know Archimedes? What's the most popular part of the story of Archimedes? Is that he running naked. Now, when we listen to his story, yeah, it's bit of crack case. Yes, that's a different story. I'll tell you so many examples. I mean, I'm not telling he's crazy. He's a genius. Sometimes when you pass some level of that smartness, you don't care about the surroundings, environment, the the places you live, the society, circumstances, you don't care about them. So he was a bit serious about his work. It was 287 BC to 212 BC. So history says he born somewhere around 287 BC. Anyway, so what is this popular story about Archimedes related to? The crown, related to the crown. So one thing is very clearly, now there was a king in Syracuse in Sicily. Syracuse is a small town in Sicily, the ancient Sicily. So they were in a war between Romans, right? And they were like a little bit good in that. And the king, Hiero II wanted to have, an interesting crown. Maybe wife forced him, because one day maybe wife saw him wearing very old-fashioned crown, and wife said, my God, look at you. Be a little bit modern and wear something better. Probably because it's he wanted to change the crown. He wanted to go for a little bit of superior one and an interesting one, not regular crown. Whenever we hear the story for the crown is like, that the crown, right? Crown is always like, we have seen these kind of, stones. So this is the boring crown we are talking about. and the stones and gems and So no, actually Archimedes wanted, sorry, the Hero wanted to have a different crown. We'll see what kind of crown it was. So when he wanted to have a good crown, he called Archimedes and asked Archimedes to make a crown for him. Archimedes is not a goldsmith, Archimedes is the scientist. Archimedes is the, actually those days he's a mathematician. So we have no like distinguish differences because philosophers say, right? So one goldsmith brought up a wonderful product and he was so happy about it. But for that, the goldsmith took some gold from the state treasure, when the king wants to have, kings are simple, kings are simple those days as well as these days, right? They have very limited requirement. What are the requirements kings have? Like good say a sword, and a palace, few palaces, big palace, right? Very simple requirements. And harem, of course, harem, antapurya, the antapurya koni. And what else? Crown, singhasanayak kone, or tunnak kone, one. So those are the requirements. Even those days, these days, no difference. They need those things to be a king. Symbols of king, right? So, and to make the crown, they gave little bit of lump of gold from the state treasure. Lump of gold from the state treasure. And when they brought the crown, probably the queen again, suspicious about the gold content in it. Say for an example, 500 grams of gold. අපිට තේරෙන විදිහට හදාගමු අපි SI system වලින් හිතමුකෝ 500 grams of gold කියලා. So අපි හිතන විදිහට 500 grams of gold ගෙනියනවා goldsmith. ගෙනිහිල්ල ඉවර වෙලා ඔටුන්න ගේනවා. ඒක 500 grams තියෙනවා. ඔටුන්නත් 500 grams. Goldsmith is also smart. But queen කල්පනා කරනවා මෙහෙමයි යන්නේ අපි කොහොමද දන්නේ මේකේ හරියටම gold තියනවද කියලා. People who know about jewelry, you know that anyway, that is the reality. We need little bit of silver, copper, kind of, metals to mix because gold is brittle, 24 karat and 22 karat. You have heard about this because you are mixing little bit. 24. As far as I know, 24 karat is the perfect gold, only gold, pure gold. But you can't make jewelries from that. So, what happened? When the crown is bought, so Archimedes was requested to check whether this is made from pure gold. And Archimedes was doing so many experiments, and one day when he was about to go to the palace, he opened the tub and opened the tap to fill the tub and let the tub to be filled completely with water and remove all the clothes. Nothing surprised because you're going to have a bath. And then he was like thinking about the crown. That's how the scientists are. That's why they're genius. Even our best thoughts coming when we are having a bath sometimes, when we go to the washroom and singing and having a good bath. So we get like nice thoughts sometimes, yes. So he was thinking and he forgot to close the tap. He forgot to close the tap. The tub fully filled and water start overflowing. When water start overflowing, He remembered, oh, I have to have a bath, and he closed the tap. Now he settled for the water, and he put one leg into the bath, and he noticed the water overflow, and it clicked the point. What was it? Why water flow? Why water overflow? Water overflow because the leg, the volume and the space concept, the leg occupies the volume inside the space of water, and now water cannot be there in the same space because water is displaced. Can you remember my first explanation about the volume and space? When I want to go there, I have to displace air and go there and get the space, occupy the space. Right? Occupy the space. So similarly, when he put the leg into water, water displaced. When water displaced, right, the leg occupied the space of water, and he got that idea. Okay, the amount of water displaced is equal to the amount of the volume of the leg. That's why water is gone out. He took the leg out, checked whether the water level, and it has gone down a little bit. He put a mark, and he put the leg again to double check whether it is rising up to the same level. Yes, it did. And he put the other leg and check water overflow again. He came out. Now he's doing the experiment. He came out, checked the level, and it has gone double downwards. Drop the water level almost double, not almost, neither. His two legs are the same size. කකුල් දෙක එක size නේ. නිසා කිසි ප්‍රශ්නයක් නැහැ. level එක බැස්ස ගන්නට දෙගුණයක් වෙන්න. Now he understand the level drops twice because why? The volume of water displaced is equal to the volume of the leg inside water. So that is the Archimedes' first invention, right? So he said, when an object partially or fully immersed in liquid, the amount of volume or the amount of liquid displaced is equal to the volume of the object inside the liquid, volume of the object inside the liquid. So this is the first part of the Archimedes principle.
And the great Archimedes, already famous during his lifetime for his scientific ingenuity. Archimedes' reputation won him a very special assignment. He had to discover whether a royal crown was made of pure gold or had been alloyed with some cheaper metal. It was a challenging task, as the precious crown could not be damaged in any way. The idea that saved Archimedes came to him in the bath. The tub was full, and when he got in, it was of pure gold. He observed that an object with a density lower than that of water latitude they discovered that the Earth is a sphere, and Ptolemy calculated the movement of the planets and other celestial bodies in relation to it. The list also includes the first steam-powered machine and the invention of the water pump. In addition, the Greeks developed equipment such as the catapult. We even owe disciplines such as geometry and algebra to the friends of wisdom.
right? So this is the crown. So you can see that it's the old golden crown, the golden crown. So it's really good, isn't it? It's very delicate, right? And you can see that they are like leaves of oak trees, and I think it's a fashion in the time of the Roman Empire, that is almost 300 BC, right? Okay. So yeah, let's line up the principle. Let's line up the principle, right? So if the crown is made out of pure gold, the crown is made out of pure gold, so you understand that the density of gold is equal to density of crown. So density means mass over mass of a crown over volume of the crown equals mass of gold over volume of gold. And you can measure the mass easily. How? Use a lever and connect 500 grams to one side, and I'm just telling the 500 grams as an example, right? Crown to the other side, yes. The volume of the crown equals volume of gold, then crown is made out of pure gold, or else crown is not. Concept number 1, when an object is completely or partially immersed in a liquid, the volume of liquid displaced is equal to the immersed volume of the object. Immersed volume of the object. Right? Concept number 2. When all this work is over, Archimedes came home and did this. The principle states that the buoyant force, the correct word is the buoyant force, the upthrust on the submerged object is equal to the weight of the liquid that is displaced by the object. Right? And it's an invention again. Experimental work. Concept part 2. The principle states that the buoyant force, the upthrust on the submerged object, is equal to the weight of the liquid that is displaced by the object. So, say for an example, an object of rho O, density of the object is rho O, volume of the object is capital V, the submerged volume of the object is simple V, density of the liquid is rho L, density of the object is rho L, and so we can say that the immersed volume of the object is V, and so that is the same amount of, that is the same volume of the object, the liquid displaced as well, right? Volume of the liquid displaced is V, and the mass of the liquid displaced is V rho L, because density into volume is mass multiplied by G, so that is the upthrust. That is the upthrust. Upthrust equals V rho L G. Right? So you can check the units and dimensions easily, right? You can check the units and dimensions. So you can see that it is a force. Upthrust is a force. Upthrust is a force. And it is a vector, and it is always acting upwards on the object. Right? Buoyant force. Buoyant force and the center of buoyancy. Right? Right. Let's check this one. Pada matak kuna. Pada matak kuna padi deval tika kiyanna, right? Archimedes principle, okay. Now, crown, and very popular spelling error you do, buoyant force. Very popular spelling mistake. Buoyant force. Oh, buoyancy. Cutting කියවෙනකොට වගේ තියෙන buoyancy නේ. But right. So the correct way is right. So the correct way is U O. Right. So now this is correct. No mistake. Buoyancy. The similar kind of thing, vacuum. Vacuum, what's the spellings of vacuum? I used to ask it in the class all the time. So when we specially mention it, you will remember this idea. Which one? Which one is the right one? At a glance, we feel like this. This is wrong. So the correct one is WM. So these are like very important simple errors we do. So yes, buoyant force and center of buoyancy. Buoyant force and center of buoyancy. Right, so let's go for the center of buoyancy is the center of gravity of the part of the object inside what. Now for an example, you can see a cylindrical object I marked. The center of gravity of the cylinder is at the geometrical center if it is a uniform rod. But when you look at the part, the immersed part, this is the immersed part. The center, geometrical center of the immersed part is here. That is called the center of buoyancy. Center of buoyancy is the geometrical center of the immersed part of the object, or we call it center of gravity of the displaced volume of the object. And the upward force UOL is the buoyant force acting on the object by the liquid. Buoyant force acting on the object by the liquid. And there must be another force, that is, say we don't call it down thrust. We don't call it down thrust. Now this blue color one is not acting on the object. It is acting on water, liquid. So downward force, and that's why the correct name is important, because this is not down thrust, we call it buoyant force. That's why the buoyant force. This is like weight. Weight එක ගැන අපි කිව්වේ gravitational force. Right? ළමෙක් දවසක් අහනවා මොකද්ද gravitational force එකේ weight එකේ වෙනස? එහෙම ලොකු වෙනසක් නැහැ. But let me tell you in a simple format, you to understand. Gravitational force is a mutual force between two objects. The popular example I take in the class, two students in the class, they attract each other, right? A to B, B to A, that's a gravitational force due to the mass in a gravitational field. But when it comes to Earth, Earth attracts all of us downwards. Downward for us because we think, we assume that we are standing straight, perpendicular. This is the upward direction. That's what we think. But that is not true, right? Isn't it? That is not true, ne? අපි ඉන්නේ නිකන් අපි හැමතිස්සෙම හිතන් හිටලා අපි ඉන්න පැත්ත උඩ පැත්ත කියලා අපි ඉන්න පැත්ත උඩ පැත්ත නෙවෙන්න පුළුවන් නේද? Now for an example, there is a person standing on earth like this. Right? Now what happened? So the gravitational force this way. Gravitational force on A by Earth this way. So the gravitational force on E by Earth this way, right? Okay. Usually Earth is a huge object. Usually Earth is a huge, massive for us, not for the solar system. Since it's a huge object and it is the mass for us. It is the mass for us. It is the mass, bigger one. ලොකුම planet එකක් අපිට නිකන් මෙයා ලොකුයි වගේ පේනවා. Right? එහෙම කතා අහනවා නේද? You are my world. කියලා වාට නිකන් පොඩි romantic එකක් ඇහුනොත් වාට නිකන් හිතන my god, that person think me really big. No, sometimes the person think about you relative to the solar system. Very small, tiny. To the universe, you are not even considered. Right, so here, so this is the one we consider as the weight. එකට අපි weight එක කියලා කියනවා. يعني Earth එකෙන් ඔයාට දෙන gravitational force එකට අපි කියන නම තමයි weight එක කියලා කියන්නේ. හැබැයි ඔගේ අනිත් එකට අපි weight එක කියන්නේ නැහැ නේ. මේකට අපි කියන්නේ නැහැ නේ weight acting on the earth by the man. එහෙම කියන්නේ නැහැ. So that's the usage. Weight is little bit coming from the domestic use, not the scientific use. Similarly, upthrust is little bit domestic, not domestic. ගෙදර නිකන් ගෙදර කුස්සිය වැඩ කර කර ඉන්නකොට අම්මා කියන්නේ අප්ට්‍රස්ට් එක මේ බලන්නකො අලගෙඩියට අප්ට්‍රස්ට් එකක් ඇවිල්ලා තිනවා කියලා. එහෙම කියන්නේ නැහැ. වතුර දාලා තිනකොට නේද? But අපි කතා කරන normal general use upthrust is the upward force, upward හින්දා කියලා කියන්නේ. හැබැයි ඒකේ original term එක වෙන්න ඕනේ buoyant force. Right? Buoyant force. Right, upthrust acting on the object by the liquid vertically upward. Yes, 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 yes. Clear. And that is called as the center of buoyancy, the point. Right. Okay. So I'll give 1 minute you to go through the note and ask any doubts you have. Please, you can drop the messages in the WhatsApp group. That is the easiest way to clarify the doubts. So please ask and go through the note and ask the doubts. Any questions? Right. Okay, now we go to the principle of flotation.
Say you're holding a slightly heavy object in your hand. Now, if you try to hold that object within a container full of water, you'll notice that it feels lighter. It doesn't feel heavy at all. What happens when you put an empty glass into a container of water? Of course, the glass fills up with water. So you're holding the glass of water inside the water which is in the container. And now, when you try to take the glass outside the water, what do you notice? Yes, the glass feels heavier when it's outside the fluid. And the same glass full of water felt light when it was placed inside the fluid. And that brings us to the concept of buoyancy. What happens when an object is placed inside a fluid? As we'd seen in the previous video, the fluid pressure increases with depth. Now, because the pressure increases as we go deeper, the force exerted upward due to the pressure will be more than the pressure exerted downwards due to the pressure. So the force exerted on the bottom of the object due to pressure will be more than the force exerted on the top. So this net upward force exerted on objects submerged in fluids is called the buoyant force. You can test this with a tightly closed empty plastic bottle and a container of water. If you drop the bottle on the fluid, you will see that it will float. That's because the fluid is applying an upward force on the bottle. Now hold the bottle and push it inside the fluid. You'd notice that the bottle is also exerting an upward force on your hand. If you leave the bottle, you'll see that the bottle will come up to the surface on its own. I think you can guess why. Now push the bottle deeper inside the fluid. You will feel more force against your hand. And when you release the bottle, it'll rush back to the surface. It'll come up faster than it came up in the previous case. The upward force increases as it's pushed deeper into the fluid. And that's because the pressure also increases as we go deeper into the fluid. This upward force exerted by the water on the bottle is known as upthrust or the buoyant force. Now let's say you simultaneously drop a piece of balsa wood and a metal drawing pin of the same mass into a container filled with water. What do you think will happen? Will both of them float? Or will they both sink? Or one stays afloat and one sinks? We will understand this example in the next video.
Right. Now, think about this. Right. Think about this. The idea right. Now, when you drop an object into a liquid, when you drop an object right into a liquid, there are 2-3 possibilities, isn't it? One, it float. We call it floating. Floating, right? The other one, this, right? The other one, this. This is sink, state of sink. This is the floating fully immersed. Floating fully immersed. It's floating, it's not going downwards. And you understand the main two out of this. So these parts, floating under different conditions, fully inside the liquid but floats. And this is completely resting at the bottom. Right. So, in these two cases, right, so we understand the two forces, only two forces there. Only two forces. So it is in equilibrium. Equilibrium, right? So in equilibrium, U equals mg. Because upward force equals downward force. This is what we call as the flotation, principle of flotation. So floating for an equilibrium, U equals mg and U equals V rho Lg. Now what is this simple V? What is this simple V? Simple V is the volume of the object immersed inside water and the volume of the water displaced. But capital V is the total volume of the object. So capital V bigger than simple V. So we can conclude what? We can conclude what? Density of the liquid is bigger than the density of the object. Go through it slowly and try to understand. Right? So, and now give me an example for this. Give me an example for this. Floating. Floating, we call it floating on the surface. Actually, it's not on the surface. Why we call it on the surface? Because yes, part of it is above, part of it is below. So the surface is kind of, you can say bent. Surface is bent to the shape of the object. Yes. The surface is touching the bottom of the object. Yes. So that is what we call as floating on the surface, right? The second case, now what are the examples of this? What are the examples for this? What are the examples of this? Simple. Ships, boats, right? Ships and boats, basically, yes. And the second one, so it is fully immersed. We call it floating, fully immersed. For equilibrium, right, again upward force equals downward force, but now in this case, it is, since it's fully immersed, the volume of the object is the volume of the immersed volume of the object. Immersed volume of the object is the volume of the object because it is fully immersed. So you can say that V cancels, density of water is equal to density of the object, and go through it and study it and finish. Right. So let me example for this floating fully immersed condition. Floating fully immersed condition. Give me an example for floating fully immersed condition. Submarines, yes, okay. Submarines are the man-made stuff. But the water, the ocean, the lakes are all about oceans and lakes, rivers, all about. What? Fish. There are a lot of fish there. And can I tell you like something very interesting fact? If, say for an example, imaginary condition, all fish in this world stay in one place in water without going up or down, just stay in one place. The funny thing, the approximate density of all fish is the same, and that is same as water. Average assumption based on, because while they are moving up and down, it's different because they adjust their density to float, because you understand the flotation principle is always, it's about floating fully immersed. Density of water is equal to density of the object. So when the fish floats, the density of fish is equal to density of water. And they maintain it. Even the huge submarines, whales, and tiny goldfish, they all have the same density when they float fully immersed. And they have the technique. Submarines, they have ballistic tanks. Fish, they have swim bladders. කරමලින් නේද? කරමලින් නේ. එයා ඒක ඇතුළට අරගෙන එයා මොකද කරන්නේ? එයාගේ බඩි වොලියුම් එක වෙනස් කරගන්නවා. ඇතුලේ තියෙන මැටීරියල් එකේ ඩෙන්සිටි එක අඩු එකක් අරගෙන එයා නේද? වෝටර් ඇතුළට අරගෙන එයා නෙමෙයි වෝටර් ඇතුළට අරගෙන එයාගේ බඩි එක බැලන්ස් කරගන්නවා. ඩෙන්සිටි එකට එයාට ෆ්ලෝට් වෙන්න ඕනේ දෙල. එයාට උඩට යන්න ඕන නම් එයා ඒක අනිත් පැත්ත කරනවා. අනිත් එක ඊට අමතරව ඒගොල්ලන්ට මේ මොනවාද පීනන්න පුළුවන් වරල් තියෙනවා නේද? That is a different story, but yeah, they do use them, but approximately they all have the same density when they just float. Swim bladders controlling the density by taking water and pumping water, taking water in and pumping water out. So that is the simple strategy to maintain the equal density to float fully immersed. The next one, sunk or completely sunk. Objects which sink and rest at the bottom. So you know that the force acting on the object upward is U plus R. So if you want to compare U, you can understand U plus R is mg, means like when you remove the R, U is smaller than mg. So U is the upthrust. Upthrust is V rho g. V is equal because same volume, right? Because it's fully immersed. It's fully immersed. When it's fully immersed, we get cancelled because it is resting at the bottom. The volume of the object is equal to volume of the object inside water because it's fully immersed. So you understand the density of liquid is smaller than density of water. So object floating fully immersed or sunk completely at the bottom. So depends on only one factor, that is density. Right? Okay. Now we are coming to the latter part of it. Right? right? So for this one, examples of this one, whatever completely immersed, sunk, resting at the bottom, examples. Rock, metal, sometimes you drop into water. In case your phone drop into water and it go and rest at the bottom. When I asked that, one student said, "Sir, Titanic, yes, all ships which were sunk in the history, so they were resting at the bottom, thousands probably, we don't know how many, right? They all rest at the bottom of the ocean. And now if you want to lift this up, what do we do? So simple process. Now we have to provide that R by some other force. For this one, right? For that one, we need to provide force up. That force balance the R. So we have like 3 natural conditions. We drop the object, it floats. It floats fully immersed. No, it is not remaining there. It go and deposit or rest at the bottom, sit at the bottom. And now you want to lift it, so you have to provide that the force required upwards. For the equilibrium of the first situation, T equals mg. So we call T as the real weight. And now we immerse the object there in water. Now we have upthrust there, but T dash is less. You can see that. Now we are lifting it up. T dash is the one we have provided to replace the normal reaction R at the bottom. So T dash is mg minus u. T dash is mg minus u. So T dash is known as what? Apparent weight. Apparent weight. Because if you look at the weight scale or the Newton balance here, so you can see that there is a difference of the reading than the previous. So that difference is upthrust. So you can say that we can develop the formula real weight minus apparent weight equals upthrust. T is the real weight, T dash is the apparent weight. So please go through it. So we'll develop the concepts to wind up the theory part, and then we'll do some questions. Right? Hope you all have gone through the full note, and now what is there to develop the concept inventory, right? So concept inventory should include all the sub lessons. I will give you the topics. Concept inventory should include right, what? Concept inventory should include number 1, number 2, principle of flotation, right? So all 3 cases one by one. The requirement for floating fully immersed and sunk at the bottom. Number 3, if you want to lift it from the bottom, so what you need to do, supply a tension and pulling it up. So then in that case we need the real depth, apparent depth formula part. So those are the 4 concepts we are learning today under Archimedes principle, right? And we'll see how does the submarine work. Right. So let's go for the past paper questions. Let's go for the past paper questions. And open the book, and there are 61 questions, right? 61 questions. Yeah, 61 questions including 2025 A-level question, right? So divide the pages as we usually work and note down these question numbers. Note down this question numbers. Yes. Right. Okay. So these are the question numbers. Please attempt them in the given order. Okay. Attempt them in the given order. Right. Keep attempting, and we'll discuss 5 by 5. And I want you to first of all divide this nicely into box pages, right? And start it now, because we are giving it, we are doing it with the correct order. So I pick the questions from Archimedes and principle of flotation. So you are doing the questions from there. So we are discussing this in the given order, and you will be understanding the concept very easily, right? Right. Start, and we'll discuss every question in every 10 minutes. Not every question in 10 minutes. 5 questions in 10 minutes. right? So yes, now we are going to start the questions, and we'll do 2 or 3 questions and go for the break. And after the break also we are doing questions, and then at the latter part we are going to do the Pascal's law, right? Yeah, so let's do the first one. I mean, question number 2, even we call it first one, it's the question number 2. लग गया दे नहीं मैं recent इंगा दे Right, so there was a small technical error. Yes, we'll go for this. A cork made of a material of density 200 kilograms per cubic meter is floating in water of density 1000 kilograms per cubic meter. The fraction of the volume of the cork not submerged in water is, so it is 1/5, 1/4, 2/5, 1/2. So now tell me, it is floating. So what's the theory? And it's the Archimedes principle. Archimedes principle, right? Principle of flotation. Upward force equals downward force, U equals mg. U equals mg. U is V rho g. U equals V rho g. U equals V rho g. V is the volume of the liquid inside, volume of the liquid inside water, volume of the first volume of water, simple V, right? Rho L is density of liquid, G is acceleration due to gravity. Capital V is total volume, rho O is volume of the object, volume of the object, right? So now the immersed volume is V minus U, sorry, V minus X. X is the volume outside the water container, right? Water surface, outside the water surface. And density is 1000 and G cancels. And now we are finding the fraction v over x. And we take v over x, we keep v over x in the left side and subtract it. Now you know the fraction is 4 over 5, simple. People who got the answers, and people who don't understand it, please tell me. I'll explain further. Right. The next one. A block of ice of constant thickness floats on seawater with 1 centimeter appearing above water level. That is question number 7. If the densities of ice and seawater are 920, 1030 respectively, the total thickness of the ice block is the same question. Only difference is the end question part. And principle of flotation says U equals mg. U is v rho lg and mg equals capital V rho g. And A into x is the cross section A. X is the volume inside water. A into x, cross section A, height x. So when it comes to the total object, total mass, capital V is cross section A into x plus 1 centimeter above water, so the total volume, and you simplify and get the answer. And there was an error in the A-level question that year, so the original paper also had the same mistake. So don't worry about it. And the total width is 9.36. Total width is 9.36. Go through it. People start communicating with me if you are watching, if you are connecting with this. So please. Right. So let's do the next one and then go to the break. A metal ball having a volume of 4 into 10 to the power minus 4 cubic meter floats at the interface of mercury and water. So water is above, mercury is below, because mercury is higher density than water. I mean, I don't know, like the practicalities, they are like that. Submerged in mercury as shown in the figure. If the densities of mercury and water 1.36 10 to the power 4 kilogram per cubic meter and 1.0 into 10 to the power 3 kilograms per cubic meter respectively, the weight of the ball in air is principle of flotation. So you understand the upthrust is in two forms, one from water, one from mercury. So the volume inside is the given half of the given volume, that given volume is 4 into 10 to the power minus 4 divided by 2 is the volume of the ball inside water, and same as in mercury. So you multiply by the densities and you get the answer 29.2 equals 10 m. M is the mass of the metal ball, 2.92. Okay, so we go for a short break and say since it's online session, I'm not going for a long break. I go for 10 minutes break. So we'll start in 10 minutes and we are going to discuss so good amount of questions, and then we'll try to learn Pascal's theory as well, Pascal's law as well, right? Okay, So let's finish this for the first session. let's continue with the questions. Now we did up to 7. Continue with the questions. 10, 15, 18. Go ahead. Right. We are gonna start and do another 3-4 questions first. Right. Okay, so it is about 1997 question number 17, the container. So we're going to do another 3 questions and give you time again, right? A cylindrical metallic vessel having thin wall, height 4h, contains water up to a height h. When immersed in water, this cylinder floats with half of its height below the water surface as shown in the figure. If the cylinder is to be floated with its almost entire height underwater, the water level inside the cylinder has to be raised from it. Now let's take this way. Now the container, so I have done it in a logical method first, and we can go with the logical method and a mathematical method separately. Logical method. Now here the container is 2h level below the water surface and h amount of water is there inside it. So first round I remove this water h out. What do you think will happen? H amount of water removed out of the container. H amount of water removed out of the container. Right? So when we remove it, what happened? It will be still H amount below. Why is that? Because H amount of water is taken out. So 2H is below because this additional H is due to the weight of the container. They call it metallic container, right? So because of the weight of the metallic container, as second diagram shows, it is H amount below. Now we try to pour water again, H amount. So it will go to 2H, and we pour another H amount, it will go to 3H, and we will pour another amount, another H amount, so it will go for 4H. Now you understand. So when you pour water up to 3H amount, we pour water up to 3H amount, so the container will be fully immersed. So this additional H amount is due to the weight of the container. The additional H amount is due to the weight of the container. Right? So I want you to draw the diagrams and explain this. Additional line you need to add. 3H amount is due to water. an H amount due to the weight of the metallic container, right. So the idea is a mathematical model, we call it delta U concept. So we understand the increase of the weight will lead to increase of the upthrust. So U1 equals M1G, U2 equals M2G. So delta U equals U1 minus U2, that is M1 minus M2G. So initial scenario, capital Mg is the weight of the container, a cross-sectional area HW is the level of water inside the container, HW. So AHW is the volume of water inside the container in the first case. So you multiply by rho W. When you multiply by rho W, so there is the mass of water inside. The right hand side of the expression, it is 2H, the volume of the container inside the liquid, and rho W is density of water, and 2HA is the volume of water displaced. And same thing we can write it for the second case. So yes, so you can subtract it. H dash is the level of water inside the container. H is the level of water initially inside the container. So you can simplify and get H dash equals 3H. Alright, let's go to the next one. Right, a boat is made of metal, floats in water with 1/5 of its volume submerged. If the second boat is made with volume 5 times bigger than the first, using the same mass of same metal that has been used to construct the first boat, the ratio of the maximum load that can be carried by the second boat, the maximum load that can carried by the first boat is equal to. So volume is 5 times, the answer is obvious, but first one 105 submerged and 104 is out. So to fully immerse this, so you know the idea, mass of the load is proportional to 4V. So the second case, mass of the load is 24. Right. So ignore the other factors, just consider the volume and mass. So M2 to M1 is 24. Why not 25 to 5? Because we have to subtract the mass of the boat. They are asking the ratio of the load. Ratio of the load. If you really want to do it in mathematical format, so what you can do is like delta M, that is the load, equals delta U. A vessel of uniform rectangular cross section with height h0 and mass m contains a certain amount of oil having mass m and density rho oil as shown in the figure. The vessel floats vertically in water of density rho w, rho oil with height h1 underwater. A certain volume of oil is now replaced by the equal volume of water. Interestingly, equal volume of water. The maximum volume of oil that can be replaced while keeping the vessel floating is V. The initial volume of oil is V0. Then the ratio V to V0 is given by. Yeah, kind of interesting. This is little bit you need to think. First line, H1, the height of the container below the water surface, multiply by the cross section A. H1A is the volume of water displaced, rho W density of water, that is H1A rho W is the volume into density, that is the mass of water displaced. And when you multiply by G, that is weight of the water displaced, is equal to upthrust, that is the weight. M plus mg. What is this capital M? The weight of the container. Simple M, the weight of liquid, sorry, weight of oil. So H0 minus H1, H0 minus H1 is the extra volume to be immersed, and when we add additional water by replacing oil, H0, now it is fully immersed. So that's why H0 minus H1. A rho Wg, V rho Wg minus V rho oil G. That is the change of mass. So let me draw a little bit of additional diagram as well, right? So a part of the container is outside, right? Some amount of oil there, right? And when it is fully immersed, by replacing oil, right? So replacing oil by water. So initially say This is mg, and oil says simple mg. Right. Now you have something, right, capital Mg there, no change. But here this part is now m dash g. So my argument is m dash g minus mg is the change in mass, that is V amount of water replaced and V amount of oil removed. So that is the change in mass, right? So change in mass is V rho W minus rho OG, right? And this change in mass caused this change in volume of immersed. So we write delta mg equals delta u. So okay, delta u equals delta mg, that is easy format. Delta u. So h naught, because initially this was h naught and this was h1. So this amount is, volume is h naught minus h1 into area, right? Area is the area of the bottom. So h naught minus h1 area and rho water g, and equals V rho W water and rho OG. So yeah. So this is what we developed, right? That is called equation 1. Okay. Right. M equals rho oil into V naught. Now that is the total mass of oil now. Now I divide 1 by 2. Why do I do that? Because I'm looking at the answer what I want. That's why sometimes people may be wondering, because I'm looking at the given answers. So I divide the equation 1 by equation 2. So I can get the reason, you understand, V over V naught. I get V over V naught. So now I have the top equation H1 A rho WG M plus mg. So subjecting A from equation A, the reason is clear, because I don't want A to be there because it's not there in the final answers. So yes, we have the final verdict. Slow but a little bit comprehensive process. Slow but little bit comprehensive process. Go through it again and again and get a screenshot of the whiteboard as well. So because I have added little bit additional information to the whiteboard. right? Do another 2 more questions. Right. Okay. So let's do one or two questions and go for Pascal's theory, and then we'll wind up the work. Water in a tank is unfortunately, sorry, water in a tank is uniformly bubbled with small identical air bubbles, each having volume V naught. As shown in the figure, a sphere of mass m and volume V floats in water, as shown due to the attachment of certain number of air bubbles on its surface. If dW is the density of water and the minimum number of bubbles that is needed to attach to keep the sphere floating in water is N. So yes, principle of flotation, upward force is upthrust equals mg. Now n number, simple n number of small air bubbles of volume V naught. So that is the total volume of the air bubble surrounding the big air bubble, and density of water, because you multiply by density of water to get the upthrust. And other than these small volumes, right? So now you know that if it is going upward, upthrust is bigger. It's going upwards, its upthrust is bigger. So N is bigger than this one, so it will go up. Right. Right. Right, when you open, now we always used to tell you physics is everything, right? Physics is everything. Physics explains everything. Physics explains everything. Everything around the world, everything around the universe, everything in day-to-day life, everything in our activities. So when you open a fizzy drink, Coca-Cola එකක් වගේ එකක් open කරාම උඩකල් තියෙනවා air bubbles මෙහෙම උඩට එනවා. Why and how these bubbles comes up, right? So simple idea, if there is an air bubble in a container, right? Air bubble in a container, so some other bubbles connecting around it, even sometimes on a wall, sometimes you may have seen like, bubble is there. I draw it a little bit large. And we see that small bubbles getting around it, right? Getting around it. And that's bubbles, after a certain point, the entire set goes up. So think that the volume of this small bubble is V naught. The big bubble is capital V. Density of the liquid is, say, rho L. And the weight of the bubble is mg. Right. Now what happened? To go up, so U must be bigger than mg, right? So U is created by upthrust. Upthrust is created by the whole volume. Say simple n number of bubbles, each bubble of volume V naught, the big bubble of capital V, okay, and displacing liquid G bigger than mg. G cancel, so you cross multiply. NV naught plus V bigger than m over rho L. So NV naught is bigger than m rho L minus capital V. You can take it V naught there as well. So in number of bubbles required, m minus V rho L divided by V naught rho L. So these are the number of bubbles. When the number of bubbles exceed, අපි බීම බෝතලයකින් ෆිසි ඩ්‍රින්ක් එකකින් කූල් ඩ්‍රින්ක් එකකින් නිකන් කාබොනේට් ඩ්‍රින්ක් එකකින් බොනකොට ඒකේ වටේ තියෙන වෝල් එකේ තියෙන එයා බබල්ස් උඩට ගැලවිලා එන්නේ කොහොමද? So simple explanation. So those bubbles attaching to the main bubble will create an upthrust bigger than the weight of the bubble. And I mean, it's a simple explanation other than the weight. So you have to consider some additional forces while it is attached to the wall as well. So we are not right now talking about it, but that's a simple strategy of motion of air bubbles connecting together, surrounded by small bubbles and going upwards. Right. Okay. So let's go for a one more question, and then we'll do the Pascal's law and finish. Right? Three masses made of materials having densities rho 1, rho 2 and rho 3 and of equal volumes are connected together with light strings. The system floats in a vessel containing two immiscible liquids of densities rho 4 and rho 5 with strings taut as shown in the figure. Consider the following conclusions made about them. Rho 1, rho 5, rho 1 smaller than rho 2, like, okay, go ahead. We'll mark the forces. So we'll mark the forces. Now we can compare rho 1 and rho 5. How do you compare rho 1 and rho 5? Because we know that rho 4 is smaller than rho 5. Rho 4 is smaller than rho 5 and rho 1 is smaller than rho 4 because rho 1 floats on rho 4. So that means rho 1 smaller than rho 4 smaller than rho 5. So rho 1 smaller than rho 5. Correct. Rho 1 smaller than rho 3. Rho 1 smaller than rho 3. Yes. Because rho 1 is there above. Rho 3 is below because the higher denser one is at the bottom. Rho 1 the object floats in. Rho 3 is at the bottom. At the bottom in the row, right? So why that order created? Because that is the heavy one, the equal volumes. If the tensions in the strings are equal, then rho 2 equals rho 5. Tensions in the strings are equal. Yes, tensions are equal. You understand, on rho 2, upthrust is equal to weight. So it is fully immersed. If it is fully immersed, so you understand the densities are equal. Yes. So yeah, that's it. Right. Okay. So continue all the questions in the list. Right. So we'll finish the final theory of Pascal. Sorry, final theory of then I think I need your support from normal place then. Is there a special folder? Normal folder, ne? Hari, okay. If I ask question, now say there is a container coming towards you. At 100 kilometers per hour. Right? Oh, it is coming towards your friend at 100 kilometers per hour, very high speed, a huge container. Right? So friend is asking for your help. Right? To stop it. What do? Are you going to help him? Are you the Superman? Do you believe if I say that, I will stop it from 1 foot? A container which is coming at 100 kilometers per hour, a huge container coming at 100 kilometers per hour in a highway. I'm going to stop it from 1 foot. Am I the Superman? No. That even you can do it. You don't have to have superpower, but you need to have a little bit of understanding of physics, because everyone in this world stopping those very high speed containers by foot, pressing the brake. Simple. Right? So how do you know that? By pressing the brake, you can stop it. Who found it? Who invented it? Applying a small force on a small cross-section area, obtaining a very large force on very large cross-sectional area. Pascal. Blaise Pascal. So let's learn that one from Blaise Pascal's theory. So what Blaise Pascal said, a pressure change at any point of an incompressible homogeneous confined fluid will be distributed everywhere in the fluid equally. right? Equally, a pressure change at any point of an incompressible homogeneous confined fluid will be distributed everywhere in fluid equally. What is meant by incompressible? Incompressible. What is incompressible? අපිට අදහස දෙන්නේ compress කරන්න බෑ වගේ එකක්. Impossible. But actually speaking, all sort of fluids in this world are compressible. The last week one student asked from me regarding this matter, "Sir, is water incompressible?" At a glance, at the basic level, we can say yes. I always tell you, like, whatever we learn as physics for A levels is slightly different when you go to the higher level. Now, incompressible means it is not possible to reduce the volume by increasing the pressure. That's the meaning of it. But in a way, all sort of fluids are compressible. The only difference is like the amount of pressure you need to provide. Like for an example, let me explain with a small example. You take air, say balloon, and you take into your hands, 2 hands, and you compress this. You can make it smaller. You can press it and make it smaller by yourself. So that is, at a glance for you, it is compressible. But when you think about the incompressibility, water kind of a thing, a syringe, you fill water from a syringe and remove the needle. I'm not talking about the syringe with the needle, syringe, and you keep the other end, the smaller side here to the finger, and press it from the other side with the piston side. So one side you close it and the other side you press it. When you press it from the piston side, will it reduce the volume? No, it is not. It won't. Why it won't? Because the pressure we provide is not large enough to compress the syringe, water in the syringe. To compress the water in the syringe, it's not possible. It's not possible for you. But say for an example, we develop a setup which is corresponding to, or which is capable of handling a large pressure. So yes, and special conditions created, you pressurize water by giving large pressure values, large changes of pressure. Again, it will compress very small amount. Most of the liquid compress by very little under huge changes of pressure. So when we don't have like a benchmark for this at the moment for A levels. So we don't set up a value, okay, below this and above that. So here my idea is generally if you can compress by the domestic conditions, school laboratory conditions, yes, that is considering as compressible fluids. If you can't compress under the normal conditions, we consider them as incompressible fluids. But even the ones we are calling as incompressible can be compressed, can be reduced, can reduce the volume by applying very large amount of pressures. So if you need very large amount of pressure changes to reduce the volume by very little, so we consider them as incompressible fluids. So I have given good example. Even air can compress 10% by just applying a small weight of an apple. So water, Water, to compress water, you need 2 Volkswagens and 1 apple. Right? So to compress diamond, even diamond can be compressed. So you need, according to the diagram, you need 8 elephants and 2 cars and 1 apple. So that's the funny illustration there. Homogeneous means the density of the fluid is the same throughout, everywhere. Uniform density throughout the liquid, or else the same liquid. Confined means, again, this is a good example for confined fluid, trapped inside. Trapped. So you can see when it is trapped, no air bubbles, no leakages. So when you push the piston from one side, the amount of fluid goes from that side to the other side is volume wise equal. So that is what we call as confined fluids. Okay. So what Pascal said is simple. We apply a force F1 on piston X with cross-sectional area A1, and we obtain a force F2. We obtain force F2 with on piston Y of cross section A2. So what Pascal said, these two are equal, and in other words, F1 over F2 equals A1 over A2. By applying a small force on large cross section, small force on small cross section, we can obtain large force on large cross section. So simply what Pascal said, by applying a small force on a small cross-sectional area, you can obtain large force on larger cross-section area. Small force, applying a small force on small cross-section, large force on large cross-section. So in a way, this is creation of force, production of force, amplification of force, amplifying the force. So you amplify the force. So that is what the Pascal's law is all about. Yes. So the applications wise, what are the applications? Hydraulic brake systems in all types of vehicles, hydraulic jacks used in vehicle service stations, hydraulic chairs used in dental clinics and modern salons. Right?
Hydraulic brake system. We all know that a car slows down and stops when we apply brakes. But how does this happen? How does the force exerted on the foot pedal stop or slow down a car? How does it multiply the force so that it is enough to stop something as big as a car? The basic idea behind any hydraulic system is very simple. The force applied at one point is transmitted to another point using an incompressible fluid, generally oil. Most brake systems also multiply the force in the process. Here you can see the simplest possible hydraulic system. Two pistons are fitted into two glass cylinders filled with oil and connected to one another with an oil-filled pipe. If you apply a downward force on one of the pistons, then the force is transmitted to the second piston through the oil in the pipe. Since oil is incompressible, the efficiency is very good. Thus, most of the applied force appears at the second piston. The advantage of hydraulic systems is that the pipe connecting the two cylinders can be of any length and shape, allowing it to choose any path separating the two pistons. The other advantage about a hydraulic system is that it multiplies the force applied.
So you can go through the full note, and there is a small question to attempt. Just do this now. You have 2 minutes to complete the question. The cross-sectional area of a tube connected to a brake pad is 1 square centimeter, and the cross-section of the tube connected to brake pads on the wheel is 50 square centimeter. To stop a vehicle, the minimum force required on the wheel by brake pads is 5 kilonewton. Find the force needed on the brake pedal to stop the vehicle. That's what I said. It's 1 square centimeter. So you can understand the force is the one we are looking for. Kilonewton force is needed on the brake pads. 5 into 10 to the power 3. So you get like 100 Newton force. That's a small force on the pedal, and that will stop the vehicle. Right? Hydraulic jack. Keep eye on it. So when you move the handle upwards, the valves, look at the valve change, that green color to red color one. So one valve opens, the other valve closed, and when you press it downwards, the valves again change and the valves open and pumping it to the middle part of the piston. So that repeats, and that will lift the red color, the large piston. So when you release the valves, it will go down and it will come to the original state. So you can see that the small piston will produce a large force on a large area. So now you can even understand how do we lift a large car or vehicle using hydraulic jacks. So service stations, right? So the valve is released, so the Hydraulic oil from the right side reservoir will come to the left side. Valve A is closed when the pressure is applied. When valve B will be open when it is pushed downwards. The hydraulic oil will go to the right side of the piston due to pressure difference, and the handle is released because of the weight of the car. So the pressure inside the piston connected to the car will go up, and valve B will be closed and valve A will be opened. So like that. Okay, so we'll discuss more questions and everything. Just that is the practical end of hydrostatics. We have done the density and the hydraulic pressure part separately. Applications, two theories, that is Archimedes theorem and Pascal's law, we have completed with that one. So now we can freely go to next month with the hydrodynamic. Probably I'll be taking hydrodynamics in the same format as well, but we wait for another 1 week. What will be the decisions happening in the country with this power crisis or the fuel crisis? So we'll plan weekly. Don't get panic. We'll go slowly, but it won't drag for a long time for sure. It will be fine in a couple of weeks. We hope for the best. And whoever doesn't like to come to the online session, whoever feel that it is not good enough for you guys, so please join the physical sessions next 2 days. That is on Saturday at Sadhana and Monday at CCG Colombo. Right. Have a good day.